Our topic is infinite series. An infinite series is a sequence of numbers whose terms are to be added up. We are aware about sequence. Let's see about the nth partial sum. Let A1, A2, A3, these are the sequence numbers. The number S, which is summation Sn, which is equal to sum of ai, where I varies from 1 to n, is called the nth partial sum of the ai's. N may be 1, 2, 3, 4. Convergent convergence of series. Let a1, a2, a3 be a sequence of numbers. The number Sn, which is already defined in the last slide, is called the nth partial sum of that of ai's. If the sequence S1, which can be obtained from this formula S2, S3 of partial sums, approach a limit S as n approaches to infinity, we say that this series converges, and we write it as that is defined as when limit n approaches to infinity of the summation of a and is called the sum of the series. This is called the sum of the series. If the series does not converge, we say that it diverges. In this case, the series has no sum. Definitely, we will not be able to find the sum of the series. We can say that a series converges if limit exists. A series diverges, limit does not exist or is infinite. Let's see an example. Write down first four partial sum of each of the following series. These are the series. We have to write down first four partial sums. S1, S2, S3, S4 are required. And we know that Sn is equal to summation of an, where n varies from 1 to infinity. We can calculate S1 from here, which is summation of A1. This is A1. This is A2, the second term. This is A3 and so on, A4 and A5. In part B, we have 1 as A1 and minus 1 by 2 as A2 plus 1 by 3 as A3 minus 1 by 4 as A4 and so on. Let's see the first four partial sum of each of the given series. S1 is 1 in part A, where S2 is the sum of first two terms, which is 3 by 2. S3 is the sum of first three terms, which is 7 by 4. And S4 is the sum of first four terms, which is 15 by 8. Similarly, in part B, we see that S1 is 1, which is 1 is the first term, S2 is partial sum of two terms, with first term is 1, second term is minus 1 by 2, so the partial sum S2 is 1 by 2, and similarly we can calculate S3 and S4. In third part, S1 is 1 and S2 is 6 by 5, S3 is 31 by 25 and S4 is 156 by 125. While if we observe the D part, which is given in summation form, we can write it in this form by expanding, because I varies from 0 to infinity. If we take I is equal to 0, we obtain this term. For I is equal to 1, we obtain this term. For I is equal to 2, we obtain this term, and so on. So now it's easy to compute the partial sums, and we can calculate S1, S2, S3 and S4. It's not difficult to find the partial sum. Let's discuss the properties of limits of sequences. Suppose that the sequences A1, A2 and so on, and B1, B2 and so on are convergent. If the sequences are convergent and that C is constant, then AN plus BN, n approaches to infinity, taking the limit, we can write separately as the limit n approaches to infinity of AN plus limit n approaches to infinity of Bn. The second property, C is constant, which is mentioned above, and the limiting value of CAN as n approaches to infinity is equal to the C times the limiting value of AN as n approaches to infinity. In third property, if we want to take the limit as n approaches to infinity of the product of A and Bn, we can take the product after taking the limit of An and Bn. Fourth property, if limit of Bn when n approaches to infinity is not equal to 0 and Bn is not equal to 0 for all n, then this limiting value can be written as in denominator and numerator separately. of an and bn. Fifth property, if f is continuous at limit n approaches to infinity of an, then the limiting value of f of an can be written as f of limit of an where n approaches to infinity. Sixth property says that limiting value of constant is the same as c, and seventh property, if we take the limit n approaches to infinity of 1 by n, this is equal to 0. In eighth property, if limit of fx is equal to L and limit of fn is equal to L, if limit of f of x is equal to L when x approaches to infinity, then limit f of n is also equal to L if n approaches to infinity. The ninth property, if the absolute value of r is less than 1, then this limiting value is 0. And if r is greater than 1 or equal to -1, then limit of Rn does not exist. This is an example to find the limit of these two parts A and B. Limit as n approaches to infinity of 3 plus n divided by 2n plus 1. And second part, sine of pi n by 2n plus 1, where n approaches to infinity. We have to evaluate the limits. This is the question. We divide the numerator and denominator by n. Or we can say that we take common n from the numerator and the denominator. Using the properties, now applying the limit, we can write it as by using the properties. We know that 2 is constant, so the limiting value of 2 is 2 according to the property, and this 3 is written outside the limit according to the property, and limiting value of 1 over n is 0. We have discussed this property also. 1 is also constant, so there will be 1 only. And again, we will write the limiting value of 1 by n as 0. Now simplifying, we obtain the value of 1 by 2. This is the solution of part A. Now we discuss the solution for the part B. We know that sin x is continuous function. We will use the property 5 to get sin pi n divided by 2 and 1 can be written as sin, and this limit will go into the bracket as n approaches to infinity of pi n divided by 2 n plus 1. we divide denominator and numerator by n, or we can take common n from the denominator and cancelling it the n mentioned in the numerator, we have this value. Now applying the limit, you see this will go to 0 and we will be left with sine pi by 2, and we are aware of that sine pi by 2 is always equal to 1. Let's return to the infinite series. Here is an series mentioned. This series, we are aware of this series. This is geometric series, and in geometric series common ratio is used which remain the same between two consecutive terms. If we take the index 0 for writing the geometric series, then A naught will be equal to 1. If 1 be equal to AR, A2 will be equal to AR for 2 and so on. And in this way, the general term will be AI, which is AR par I. And in compact form, we can write it in this way. Also, we may replace the index I by any other letter. Just if we see I is equal to 1 to infinity, or j is equal to 1 to infinity, or we can write it as n is equal to 1 to infinity. And so to find the sum of a geometric series, we must first evaluate the partial sum. We know that partial sum Sn is equal to sum of AR bar I, where I varies from 0 to n. We can write S if we expand here, where I varies from 0 to n, we obtain A plus AR square up to AR bar n. And if we multiply R with above equation, we obtain this relation. Now, if we subtract the second equation from the first and solving for Sn, we obtain this relation. If R is not equal to 1, the sum of the entire series is the limit of SR as n approaches to infinity. Again, limit n approaches to infinity, Sn is mentioned here. We replace it here and simplifying we obtain this constant A by 1 minus R, limit n approaches to infinity of 1 minus R n plus 1, which is again written in this form. If R is less than 1, then this limiting value will be equal to 0 according to the properties. So in this case, this summation is convergent if the sum and its sum is a by 1 minus r. If r is greater than 1 or r is equal to minus 1, then this limit does not exist according to the property number 9. And so, if a is not equal to 0, the series diverges. Finally, if r is equal